As in previous years, the slides will be indicated by a colour icon, depending on what relevant volume that we're discussing and that changes refer to. Please note that all the changes to volume 1 will be reflected in the guide, but if we're talking about a change to the guide only, then it will be the guide image that's shown on the slides. Also, as always, the adoption date is the 1st of May, and this year it falls on a Friday. First is the definition of swimming pool. A recent magistrate's decision determined that a swimming pool manufactured by a well-known pool company was not a swimming pool for the purpose of fencing requirements, because they upheld that the owner's argument that the swimming pool was used as a water storage tank for firefighting purposes and not principally or primarily used for swimming. The magistrate read the term used principally or used primarily for swimming, etc., as meaning that the pool needed to be used more than 50% of the time for swimming to be considered a swimming pool for which a barrier was required. The change to the definition in the BCA 2015 removes the emphasis on the primary use of the pool and instead emphasises its intended use at the design or construction stage. It clarifies the intent that structures designed and manufactured as swimming pools, even those used for alternative purposes, are still required to be fenced, as they present the same attraction and hazard to young children. The change will now also align the NCC definition more closely with other states and territory definitions of swimming pools. You might ask why we don't just remove the term principally or primarily from the definition. Well, its retention is excluding structures that are not currently considered to be a swimming pool. For example, a farm dam may be primarily used for stock watering or irrigation, therefore excluded by the current definition, but be occasionally used for swimming, potentially caught by the proposed definition. Also, the proposed wording does not cover the situation where excavations or structures are not originally designed or constructed as swimming pools, but are adapted for the use. For example, the skip in the photo. The next change relates to the application of the NCC to multi-classified buildings. Building classifications are used in the NCC to categorise buildings of similar risk levels based on use, hazard and occupancy. NCC requirements are then applied on the basis of those classifications. With the growing trend for buildings containing multiple classifications, a number of examples have been provided where the intent of the current wording in the NCC is considered unclear in whether the requirements of a building of a particular classification apply only to part of the building or to the whole building. A wording of A1.7 is open to interpretation to accommodate the different circumstance in which the term building is used in the BCA. This openness, however, seems to be providing undue discretion to users when determining whether a reference to a building is the entire building or part of a building. For example, a building surveyor may at their discretion require a provision to be applied to the entire building instead of only to the relevant part, should they think this expedient. This level of discretion is not considered to reflect the intent of the provisions. As noted in the guide, wording for A1.7, unless the contrary intention appears, i.e. there is a specific reference to the whole building, a reference to a building in the BCA is a reference to the relevant part of the building. This means that each part of the building must comply with the relevant provisions for its classification. To assist in the correct application of multi-classified buildings, changes have occurred to A3.3 as well as A1.7. A new subclause, A3.3c, reinforces the understanding that a building, unless a contrary intention is stated, is made up of various parts or classifications within the building, and each part, unless the contrary is stated, should comply with the relevant provisions for that classification. A building is therefore simply a collection of classification building blocks. So with this understanding, let's consider the fire sprinkler provisions for a theatre located in a building less than 25 metres in height. Table E 1.5, by reference to Part H1, requires a fire sprinkler to be applied to the Class 9B theatre. So for this described situation, where the building is less than 25 metres in height, its application is only to the Class 9B part of the building, not to the whole building. However, in a building higher than 25 metres, the fire sprinkler provisions of E 1.5 provide an example of where the contrary intention appears, and we have a reference to the whole building. The application requires sprinklers throughout the whole building, which encompasses all the building classes and parts in the structure. So the general rule is establish the various individual classifications of the building and apply the relevant BCA provisions applicable to only the relevant part or classification of the building, unless the BCA provision specifically requires its application to the entire building. The above example provides an application to the whole building to explain where the contrary intention may apply. However, it may, in some circumstances, require consideration of other components of the building, such as a fire compartment, rather than the whole building. BCA 2015 sees the continuation of the quantification of performance program by the ABCB. This year, verification method BV1 and V2.2.1 have been introduced to quantify structural reliability performance. The verification method may be used by designers if they wish to operate outside the deemed to satisfy and demonstrate compliance with the performance requirements BP 1.1 and BP 1.2. The new verification method could be used to demonstrate that a new material like CLT, a composite material like styrofoam cladding, or an old material used in a new way meets the NCC performance requirements. BV1 and V2.1.1 are designed to support alternative solutions. It's important to note that these verification methods are primarily intended for use by engineers or product manufacturers. Compliance with BP 1.1 and BP 1.2 is verified for the design of the structural components and connections when the calculated annual structural reliability index for each action is not less than that listed in table BV 1.1, and the annual structural reliability index is calculated in accordance with the displayed formula. The verification method applies to the structural reliability of all structural components and connections within a building. However, contained in the note to the table, there is a concession for structural components and connections that are not primary structural components or connections. Primary structural components or connections are those whose failure could result in the collapse of the building, structure itself, or collapse of other property, which by definition would include a structure, a building, road, or an allotment that may adjoin this building. These components should attain the unadjusted values of table BV 1.1. The structural reliability indices for all other components or connections in the structural system that do not affect the collapse of the building, structure, or other property can be reduced by 0.3. Consultation with an engineer, product manufacturer should be used to determine what is considered primary for that product and design. The ABCB has produced a YouTube clip along with a comprehensive information handbook to help practitioners use the verification method. Both of them can be found on the ABCB's website. I can play the lovely YouTube videos that we've got just to keep you amused for a minute.
A verification method is one of many optional assessment methods available in the National Construction Code, or NCC. However, it is not a mandatory requirement. Verification methods may be used as part of a performance solution to assess compliance with specific performance requirements. The NCC contains verification methods to assess structural reliability and demonstrate compliance with specific structural performance requirements for both commercial and residential buildings. A design is acceptable when it meets the structural reliability targets. The verification methods provide the required targets for each action type affecting a building, permanent and imposed actions, or environmental actions, which are wind, earthquake, and snow. These clear targets allow a designer to assess a design based on material properties and is particularly useful for innovative designs and materials which have no deemed to satisfy provisions. The verification methods are based on probability theory. For designers, this involves assessing the probability of failure of a building component or connection. When assessing a component, action effects working against the building are represented as Q, and the structural resistance of the building is represented as R. The probability of failure of the building is the probability that the resistance is less than the action on the building, or R is less than Q. The verification methods are satisfied when the resistance of the components is greater than the actions against the components. To evaluate structural reliability, the relationship between actions and resistance is assessed. Actions and resistances are represented by log normal distributions. The action distribution has the following variables. The most frequent value of the action is the peak of the curve. The nominal design value of the action is usually a high percentile value. The variation of the action is the spread of the curve. In order to calculate the target reliability, the coefficient of the action is required. The resistance distribution has similar variables, where the most frequent value of the resistance is the peak of the curve. The nominal design value of the resistance is a 5 percentile value. The variation of the resistance is the spread of the curve. Similarly to the action variables, the coefficient of the resistance is required. Collectively, these are the action and resistance variables for the calculation of structural reliability. The verification methods constrain the action variables by providing the mean action and variation of the action. The remaining variables for assessment are related only to resistance, where the resistance needs to exceed the nominal design value of the action. These values are determined by the material testing of the design component or connection. To evaluate the action and resistance distributions, the structural reliability index, beta, is equal to the inverse of negative capital Phi multiplied by the probability of failure, where capital Phi is equal to the inverse standardized normal distribution. A load factor provides tolerance for unknown variables in the data and is represented by gamma. A capacity factor, represented by Phi, allows for the difference between the real capacity of the material and the theoretical capacity to ensure design loads are achieved. To determine the ratio of the mean of resistance to the mean of the action for each design scenario, equate the mean resistance over the mean action with respect to the nominal design values and the load and capacity factors. The structural reliability can then be calculated by taking the natural log of the mean resistance over the mean action multiplied by the square root of the coefficient of the action over the coefficient of the resistance, all divided by the square root of the natural log of the coefficient of the resistance multiplied by the coefficient of the action. The structural verification method is an optional assessment method that can be used to determine compliance with the performance requirements, allowing for innovative designs and materials to be used.